Hey guys, I'm Christian and today I'm going to teach you how to solve parametric equations. So, what is a parametric? A parametric is defined as a type of equation that represents x and y in terms of a parameter, and you'll often see this parameter be represented by t. For example, you'll see x of t equals, say, 3t minus 1, and y of t equals 5t squared plus 3. This is just an example, but as you can see here, rather than y being dependent on x, both are dependent on the parameter t. For example, if t were to equal -2, the value of x of t and y of t would be different from each other. And this is often useful in cases such as physics, where you might need t as a parameter of time, and the x value dependent on time will be different from the y value. Even though x and y have their own equations in terms of t, there still is a relationship between x and y. And oftentimes, we want to set parametrics up in terms of x related to y or vice versa, because that's what we're more familiar with. So in order to do that, you just treat this like a system of equations. If you want to get x substituted into the y equation, you would just start over on x side and get t by itself. So first, add 3 to each side. And then you would divide both sides by 2. Now you have t in terms of x. So now that you have this, you can substitute that x plus 3 over 2 into the y equation for t because it's equal to it, just like a regular substitution problem. And then you just multiply that all out to get it most simply in terms of x. And there you have it. That's your simplified parametric equation version of y in terms of x for this problem. Now you might have noticed something weird in the corner over there, and that's a restriction on t. That's sort of like a domain restriction, except it's in terms of t. So in order to make it more understandable to us, we'll put it in terms of x in a much similar way that we just plugged x into the y equation. So over here, since x plus 3 over 2 is equal to t, we're just going to plug in x plus 3 over 2 into t over here, like so. Now, as you can see, that's pretty ugly, and that's not how we want to leave our domain. So we'll simplify the x by first multiplying 2 to either side of the domain, to get rid of the denominator on x. And then subtract 3 to get x by itself. And there you have it. Alright, let's take a look at a slightly more challenging example, though this one does not have a limitation on t, so that helps out a little bit. So first, we're going to try to do what we did in the last problem and get t isolated and get it in terms of x. So we'll start by adding 1 to each side. then dividing by 5. But now, we're kind of at a dead end. We could take inverse sine of the left side, but then that wouldn't really be that pretty to plug into the y equation. So let's see if maybe we have some better luck with the y equation. Subtract 2 from each side. And then divide by 2. And then it looks like we got the same thing going on the y side too. So what would the best way to do this be? Well, remember our trigger identity. Sine squared of t plus cosine squared of t, or any variable really, is equal to 1. So if we square this, which is pretty much squaring cosine of t, and we square this, which is equal to sine squared of t, then x plus 1 over 5 squared plus y minus 2 over 2 squared is equal to sine squared of t, because sine squared of t is that x plus 1 over 5 plus cosine squared of t, because the cosine squared of t is the same as the y minus 2 over 2. And all of that is equal to 1. So our real equation here without t would be x plus 1 over 5 squared plus y minus 2 over 2 squared equals 1. And that looks like the graph of either a hyperbola or ellipse. Forgive me, Miss Porter, I'm not remembering which one it is, but it's one of the two. And that's the best way to approach an equation like that with a parameter. A useful application of parametrics is projectile motion, which uses the parameter t, or time, to find how far an object traveled horizontally, vertically, or both, given equations set in terms of time, rather than x and y. For example, depending on the angle that it is launched from the ground, the horizontal distance that it travels can be modeled by the equation x of t, or time, equals time times initial velocity times cosine of theta, of where theta is that angle from the ground that the projectile is launched. And you know that cosine of theta from the unit circle goes with x, which is why it goes with the horizontal distance traveled. And for the vertical distance, the equation is a little bit more complicated, but similar, where y of t equals t times the same initial velocity that you saw in the x equation, times sine of theta instead of cosine of theta, because it goes with y, minus 1/2 the gravitational constant, or how fast gravity makes things travel vertically, times t squared, plus the initial height, or ho. Let's take a look at an example of using parametrics to represent projectile motion. So, as you can see here, Tom and Sarah are playing catch. Tom tosses a ball to Sarah at an initial velocity of 38 feet per second at an angle of 28 degrees from a height of 4 feet. Sarah is 40 feet away from Tom. And the first question is asking, how high will the ball be above the ground when the ball gets to Sarah? So this looks like a lot of information, but all this is really doing is giving us a bunch of numbers that we can plug in to our somewhat complicated projectile motion equations. Me personally, I don't have those memorized, so I'm going to reference those very quickly, but our first step is going to be to plug in all of these numbers into those equations. So first, we're going to get the horizontal equation, though you can do vertical first, whichever order you would like. X of t equals t, which we're not sure what t is yet, times initial velocity, which is 38 feet per second, times cosine of theta, which in this case the theta gives us is 28 degrees. For our vertical distance equation, y of t equals t, let's see, times 38 feet per second times sine of theta, we'll just use the same theta as it gave us for the x, minus 1/2, and then this is where you have to use a gravitational constant. But I want to clarify something that I said in a previous portion of this video where the gravitational constant is 9.8. That's for meters per second. If you're using feet per second, then you instead would use 32. So because this problem is given to us in feet per second, we want to keep the units consistent. We're going to use 32 for our gravitational constant here. And then times t squared, we don't know t yet, plus 4, because that's the initial height. Now that we have our equations, the next step of this problem would be to simply look at what we're looking for. So, step 2, this is pretty much asking us to put this in terms of our equation. What is y? So what is the y of t equation when x, or the horizontal distance equation, is equal to 40? Because even though the words this problem uses is how high will the ball be above the ground when it gets to Sarah, what we want to understand from this, from a parametric equation standpoint, is how high is the ball when the horizontal distance reaches 40 feet, because they're 40 feet away from each other. However, for the y equation, this x value doesn't help us very much because it's in terms of t. So what we can do is set the horizontal distance equation equal to 40 to find the t, because whatever the t is, however long it took the ball to travel 40 feet horizontally, that will also, we can plug that same time into the y equation to find out what the height is at 40 feet of horizontal distance traveled, So, now that we've identified what we're looking for, we can set 40 is equal to t times 38 times cosine of 28 squared. Now this here to find t is just simple algebra, so you can plug that into your calculator and you get roughly 1.51 seconds as the time it took for the ball to travel 40 feet. Now, with this time, we can plug it into the y equation and figure out how high the ball was at this time, or in other words, how high the ball was when it had traveled 40 feet. So, our final step, let me move over here for that, is going to be plugging that t into the vertical distance equation. So y of 1.51 equals 1.51 times 38 times sine of 28 minus 1/2 32, or just 16, t squared plus 4. Or excuse me, not t squared, 1.51 squared plus 4. When you plug that all into your calculator, 2.53 feet. And that is your final answer to that problem. How high will the ball be when Sarah gets it? For the next part of the problem, we're going to be looking at the y equation, or the vertical distance, to find the maximum height of the ball. So the trick to this one is the y equation can be written as a polynomial. Y of t equals, if you're looking at that, 16t squared or negative 16t squared, plus 38 sine of 28t, which if we plug into our calculator gives us 33.55 t, and plus 4, and that's our polynomial. So what can we get from this? Well, the secret is projectile motion problems are really just a parabola, because many objects travel in a parabola like so. Go up a little bit and then come back down. And if you're finding the vertex of a parabola, the equation is vertex equals negative b over 2a. So if we want to find the highest the ball travels in this parabola, we just simply plug in from this polynomial to find the time at which the ball was the highest. So if we plug into that equation, we get negative 33.55 over 2a, or just negative 32. Then the negatives cancel, and we get approximately 0.322 seconds as the time where our ball reaches the highest height in that throw. And then you can probably guess where you go from that. Now you have a t, and to find the actual distance, you plug it back into the y equation. So y of 0.322 equals 0.322 times 38 times sine of 28 minus 16, 0.322 squared plus 4. And I'll save you guys the time. I've already punched that in my calculator. And for your height, at the time where the ball is at its highest, the vertical distance is 5.66 feet. And that's how you solve that one.